तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Looked at certain important properties of Laplace transforms in the last lecture. The particular properties which are of interest are those when f of t gets multiplied by t, what happens in the transform domain. If f of t is differentiated, if f of t is integrated, their effects in the transform domain are three important properties which we discussed in the last lecture. We will continue this discussion of the properties of Laplace transforms, which will be useful when we handle problems involving the application of Laplace transforms to the solution of electrical networks and systems under dynamic conditions. So, let us consider now the next property, which concerns what is called shift in frequency. Shift in frequency domain, that is S domain, which is equivalent to multiplication by an exponent, multiplication by an exponent exponential function in time domain. What we are going to show is that if you multiply an f of t by an exponential function like e to the power of minus alpha t, it corresponds to a shift in the frequency domain, that is the S plane or S domain. Let us consider an f of t whose Laplace transform is f of s. The question which we would like to ask is, what is the Laplace transform of f of t multiplied by e to the power of minus zt, assuming all these, of course assuming that f of t is a causal time function. What is it equal to? To make for generality, z can be complex. So, this is the what we are going to look at. So, to using the formula for the Laplace transform of a time function, this particular Laplace transform would be from 0 to infinity f of t e to the power of minus zt e to the power of minus st dt. I am not putting specifically 0 minus, because depending upon our interest, whether you take from 0 minus or 0 plus, depending upon what you take f of t to be, the type of f of t that you are interested in. So, we will leave it at that. This of course can be written as 0 to infinity of f of t e to the power of minus of s plus z t dt. Now, you see that if it had been e to the power of minus st dt, f t e to the power of minus st dt integral will be f of s. All we have now is instead of s, we have s plus z. So, if it had been f of t e to the power of minus st dt, this would have been capital F of s. This is Laplace transform of f of t. Now, instead of the variable s, we have s plus z. So, this will be f of s plus z. So, we have, if f of t has the Laplace transform f of s, if you multiply f of t by e to the power of minus zt, the Laplace transform is simply f of s plus z. That means this is a translation or shift in the frequency domain. So this is a very important property which will be found quite useful in finding out the Laplace transform of certain time functions as well as the inverse Laplace transforms of certain functions of s. And of course, in the new function that you are having, the abscissa of convergence, whatever it was for f of t, will get modified because of this, the factor e to the power of minus zt. Depending upon the real value of z, then the abscissa of convergence can be modified for the new function, but that is not important for us. We note, of course, that it is possible that the abscissa of convergence of the new function will be different from the abscissa of convergence for the original f of t. Let me take an example. Suppose we have u of t, we know that its Laplace transform is 1 over s. Now, let me multiply u of t by e to the power of minus alpha t. So, according to this rule, instead of s, we have to replace s plus alpha. That is all that we have to do. Therefore, this is 1 over s plus alpha. So, in other words, e to the power of minus alpha t ut, which we have derived earlier from fundamentals, could have been derived using the applying this particular rule of shift in frequency domain corresponding to a multiplication by e to the power of minus alpha t. Now, let me take another example. Suppose I have cos omega naught t ut, a cosine function. We know its Laplace transform is s over s squared plus omega naught squared. That would be a cosine, a trigonometric function which starts from t equals 0. On the other hand, suppose I take e to the power of minus alpha t cos omega naught t ut. This particular time function is again oscillatory, but with decreasing amplitude depending upon this value of alpha. So, its plot would be, if this is the envelope, so you have something like this, where the amplitudes decay as e to the power of minus alpha t. So, an exponentially damped sinusoidal function of time. Now, all this differs from the original function is by multiplication by e to the power of minus alpha t. Therefore, according to this rule, all we have to do is replace s by s plus alpha. So, we have s plus alpha divided by s plus alpha squared omega naught squared. So, this gives you a new function of time Laplace transform pair. E to the power of minus alpha t cos omega naught t ut will be s plus alpha over s plus alpha squared plus omega naught squared. We do not have to remember this, because once you know the formula, the Laplace transform of cos omega naught t, whenever it gets multiplied by an exponential factor by that, you should be able to readily reduce this. But nevertheless, let me put this down in our table of Laplace transform and f of t pairs. I will go to the other end of the blackboard, even if our cameraman will frown at this, but let me do that, I will take that risk. So, we have e to the power of minus alpha t cos omega naught t ut will have a Laplace transform s over alpha over s plus alpha squared plus omega naught squared. In the same manner, suppose I have e to the power of minus alpha t sin omega naught t ut. We know that the Laplace transform of sin omega naught t ut is omega naught over s squared plus omega naught squared. So, in that particular function, we have to substitute s plus alpha for s. So, omega naught will remain as before. The denominator will be s plus alpha squared omega naught squared. So, that would be the Laplace transform e to the power of minus alpha t sin omega naught t ut. Visualizing this in this fashion will be very important when you are taking sometimes inverse Laplace transform of functions where a quadratic exists in the denominator. For example, suppose I ask the question, what is the inverse Laplace transform of, say, s plus 1 over s squared plus s plus 1? Suppose I ask this question. Now, note that the poles of this rational function or the zeros of the denominator polynomial are complex. In that case, s squared plus s plus 1 can be put in this form s plus alpha square, s plus alpha whole square plus omega naught squared. If you try to put that in that form, then you can combine, you can decompose this function into sum of two such functions, and then you can readily recognize them to be the inverse Laplace transforms of sinusoidal functions with decreasing amplitude. So let us go about it. Let's see this. So s plus 1 over s squared plus s plus 1. First of all, I should write this in the denominator as s plus alpha whole squared plus omega naught squared. Therefore, I write this s plus half whole squared, so that accounts for the coefficient of s here, s squared plus s plus 1/4, but still you have 1 here. Therefore, to cover that, I will put this root 3 by 2 whole square. So you observe that 3/4 plus 1/4 is equal to 1, and therefore we have this, the complex conjugate poles of the function are clearly displayed as minus half plus or minus j root 3 by 2. Now, if the numerator has been s plus half, we would have identified this to be e to the power of minus half t cos root 3 by 2. Therefore, let us do that. So you have s plus half divided by s plus half whole squared plus root 3 by 2 whole squared. This is one term, and what is left behind is another half here. If the numerator has been a constant root 3 by 2, then we would have put this as e to the power of minus alpha t sin omega naught t by 2. So if this had been root 3 by 2 divided by s plus half whole squared plus root 3 by 2 whole squared, then we would have said this to be the Laplace transform of e to the power of minus half t times sin root 3 upon 2 t. But we had only half here, therefore to cover that we must put 1 over root 3. Then you have s plus half. This term we know is the Laplace transform of e to the power of minus t by 2 cos root 3 by 2 t, and this term will be 1 over root 3 e to the power of minus t upon 2 sin root 3 by 2 t, and of course the entire thing is multiplied by u of t. That is the f of t, which corresponds to this Laplace transformation. So this rule of what happens when you multiply the time function by an exponent will come in handy not only in finding the Laplace transforms of certain time functions, but when you are finding the inverse Laplace transform of quadratic factors where the denominator zeros or complex conjugates can be easily be handled in this fashion. The rule we have considered just now is that if f of t is multiplied by an exponential function of time, that corresponds to a shift in the frequency domain. We have a dual rule which corresponds to shift in time domain, and that corresponds to multiplication by an exponential function in the frequency domain. This is corresponds to multiplication by an exponential function in the frequency domain, that is the complex frequency domain, or in S domain. Let me first put down the rule and then we will try to demonstrate that. Suppose f of t and f of s form a transform pair, and let me assume that I will also put u of t to make sure that it is a causal function. Suppose I have this is f of t u t. Now let me say that I translate this, I delay this function of time by an amount of tau seconds. So, instead of starting from t equals 0, it starts from here and it goes like this. So, this is tau. The same function is delayed by an amount tau. Therefore, we can describe this as f of t minus tau u of t minus tau. This is the description of this function. Everything is delayed by tau seconds. Whatever value this function takes at t1, this will take at this t1 plus tau seconds in the second case. It is delayed. So, what is the Laplace transform of, given the Laplace transform of this is f of s, we ask the question, what is the Laplace transform of this? So, f of t minus tau u of t minus tau has the Laplace transform. It turns out to be e to the power of minus tau s f of s. So, a shift in the time domain corresponds to multiplication by an exponential factor in the frequency domain. A delay by tau seconds involves multiplication in the frequency domain by e to the power of minus tau s. We take tau to be greater than 0, that is, this corresponds to a delay. Now, the proof of this is quite straightforward. So, we are interested in finding the Laplace transform of f of t minus tau u of t minus tau, and this must be multiplied by e to the power of minus st dt. That is what we are interested in finding. Now, since the variable of integration is t, as long as t is less than tau, u of t minus tau is 0. So, as long as t is less than tau, the argument is negative and this makes it 0. Therefore, I can as well start the integration from tau infinity of f of t minus tau u of t minus tau e to the power of minus st dt, because this factor makes the integrand 0 for values of t up to equal tau. Therefore, f of t minus tau u t minus tau e to the power of minus st dt. And for values of t larger than tau, then this is going to be 1. So, you may as well leave it like that, or you may, even if you want to keep it, no harm in there, no harm is there. Now, let me put here t minus tau as, let us say, x. Then this is f of x, u of x, e to the power of minus s, t equals tau plus x, x plus tau, and the dt equals dx. And the range of integration, now when t becomes tau, x becomes 0, so it starts from 0, and when t equals infinity, x also will be infinity because tau is finite. That is what we are having. Now, this integral involves the variable of integration x. This tau is a constant, therefore, I can write this as e to the power of minus s tau 0 to infinity of f of x e to the power of minus sx dx. And what you are having here is indeed, you can also consider this 0 to infinity f of t e to the power of minus st dt. So, that is the Laplace transform of f of t. Therefore, the result is e to the power of minus s tau f of s. This is what we mentioned here as the Laplace transform of f of t minus tau u to t minus tau. That is the proof of this. This particular rule is very, very important because it comes in very, very handy in finding out the Laplace transforms of various typical functions that we handle, like pulse functions and so on. As we will take some examples to illustrate this. Let us see, let us work out some examples. Let us consider first of all a pulse function 0 to d. It exists from 0 to d, value a here. This is f of t. Now, you can always consider this pulse to be a step function of amplitude a starting at t equals 0 plus another step function of amplitude minus a starting at time t equals d. If you add these two step functions, one regular step function starting at t equals 0, another a delayed step function starting at t equals d, adding up these two you will get this. And now we know the Laplace transform of this. This will be, this is a not a unit step function, but a step function of amplitude or magnitude a. Therefore, the Laplace transform of this is a upon s. Now, the Laplace transform of this is, how do you describe this? Is this minus a u of t minus d. This is the expression for this second function, whereas the first function is a u of t, and therefore it had this Laplace transform. All we are now doing is, instead of t, you are delaying this by d seconds. Therefore, the Laplace transform of u of t minus d is 1 over s e to the power of minus ds. You are multiplying this by a minus a. Therefore, the Laplace transform of this is minus a by s. This would have been the Laplace transform if this delay did not occur, but because the delay, you have e to the power of minus ds. Therefore, the Laplace transform of this is the sum of these two. So, you have a upon s into 1 minus e to the power of minus ds. That is the Laplace transform of this. So, you observe that whenever you have discontinuities in the function and type of pulse functions like this, they can quite conveniently handled by using this property of the shift in time domain. What difference it makes in the transform domain is, all that it means is you are multiplying by an exponential factor e to the power of minus s times the delay that is involved. Let me take another example. B. Suppose I have 1/2 cycle of a sinusoid, just this 0 to t naught upon 2, and of course we'll assume that omega naught equals 2 pi upon t naught. So, we want to find out the Laplace transform of this, a single loop of a sinusoid. Now, this can be considered to be a regular sinusoid sin omega naught t ut plus, suppose I delay this sinusoid by 1/2 period. So, I get another sinusoid like this, and this would be sin omega naught t minus t naught upon 2 delayed by that amount u of t minus t naught upon 2. That is a delayed sinusoid. Now, if you add these two, this negative loop is cancelled by the positive loop, this positive loop is cancelled by the negative loop, and so on. If you add these two, this is what you get, right? And therefore, if you add the Laplace transforms of these two, you will get the Laplace transform of this by the linearity principle which we talked about. Okay. Therefore, the Laplace transform of this single loop will be the Laplace transform of this, which is omega naught over s squared plus omega naught squared, plus the Laplace transform of this, which is obtained by multiplying the Laplace transform of this by e to the power of s times minus s times the delay that is involved. Therefore, e to the power of minus s t naught upon 2. That is what you are having. That is the Laplace transform of this single loop. You don't have to do any integration. The advantage of knowing all these properties is that whenever you are having functions of this type, if you cleverly manipulate this, you don't have to carry out this integration to find out the Laplace transforms. From the Laplace transforms of known functions, you can construct the Laplace transform of this purely through algebraic procedures as shown here. So, let us move on. Let me consider two further examples. 1. Suppose I have a triangular pulse function 0 to 4 seconds, it lasts, it reaches a value of 8 at t equals 4, and we would like to find out the Laplace transform of this. Now once again we do not have to do any integration, because we know the Laplace transforms of ramp functions and step functions. So we would like to decompose this function in terms of appropriate step and ramp functions. Let us see how we do that. Suppose we describe this portion by a ramp function, then you have a ramp starting at 0, reaching the value 8 at time t equals 4, and this would be described as 8 units, it jumps by 8 units in 4 seconds, therefore it is a slope of 2, so this will be 2 times RT, that would be the ramp. Now this ramp describes the actual behavior of f of t up to t equals 4 seconds, but at this point we must nullify whatever is left beyond 4. So to do that we introduce a negative ramp here at 4 seconds of the same slope, so that the growth is arrested. Therefore this would be having the negative slope of -2, and then it starts at t equals 4 seconds. So that would be the description of this curve. -2 RT minus 4 would be a negative going ramp with a slope of magnitude 2 starting at t equals 4. If you added these two, what you would get is this one plus a constant here, because whatever increase here is cancelled by the increase here. So what is left by adding these two curves is not only this triangular pulse, but also a kind of constant, a step here. So we should cancel that step as well, and the magnitude of the step is 8 units and starts at 4. So in addition we need to have a step here, a negative step. So this will be described as -8 u of t minus 4. So if you added these three characteristics, then you would get this pulse. You have a ramp function to start with, a negative ramp to arrest the growth, and then afterwards whatever amount to which it has grown must also be cancelled out, that will be -8 u to the power of t minus 4. Now we know the Laplace transforms of these three type functions. So the Laplace transform of this would be the Laplace transform of the ramp, which is 2 upon s squared, and then the Laplace transform of this ramp is, if this is 2 upon s squared, this is 2 upon s squared times e to the power of minus 4s, because the same ramp with a negative sign and delayed by 4 seconds. Therefore minus 2 upon s squared e to the power of minus 4s. That would be the Laplace transform of this delayed ramp. The Laplace transform of this step function is -8. It would have been, if it had started at t equals 0, it would have been -8 by s, but since it has been delayed by 4 seconds, you have to write -8 by s e to the power of minus 4s. That is what we are having, 2 upon s squared times 1 minus e to the power of minus 4s minus 8s over e to the power of minus 4. This is the how it goes. Second example. Now you must be careful when we are talking about the notation for the delayed time functions, that you f of t minus tau times u of t minus tau is gives a proper expression for the delayed time functions. To distinguish between other possibilities, let me take a set of examples. This would be TUT. Suppose f of t is t, then this is 2ut. Suppose I write t minus 1 u of t. What does it mean? This is not a delayed function, because u of t has not been replaced by u of t minus 1. T minus 1 ut would be this function 1, this will be at t equals 0 it would have been minus 1, that is what it would be. The same slope of course, but it does not start at t equals 1. This is not a delayed version of this, important to recognize that. Suppose I have t ut minus 1. So this is t ut, but t is multiplied by ut minus 1. That means this function t is multiplied by a step which is starting at t equals 1 at this point. Therefore, this would have been t, but this portion has been cut off. So that would be t ut minus 1. So this is 1, and here it is. That is t ut minus 1. On the other hand, if you have t minus 1, ut minus 1, this would be whatever sequence of values this had, it takes 1 second later. Therefore, this is a proper delayed function. The same function is delayed by 1 second. Therefore, that could be. So you see, you have presumably these are delayed functions, but they are not the delayed functions of this. So we must be careful in distinguishing between the various functions that are covered by these expressions. Now the Laplace transform of this is of course 1 over s squared. It's very clear. Now this is a delayed function, therefore you can immediately write 1 over s squared e to the power of delay is 1 second, therefore 1 over s squared e to the power of minus s. There is no problem about that. Now what about this? T minus 1 ut can be written as t ut minus ut. T ut, that means you have t ut, you remove one unit value at every point of time, this is what you get. T ut would be this curve parallel to this. If you remove u of t from that, this curve results. Therefore, the Laplace transform of this is 1 over s squared minus 1 over s. The Laplace transform of t ut is 1 over s squared, Laplace transform of ut is 1 over s. Now as far as this is concerned, t ut minus 1, you can think of this as t minus 1 ut minus 1 plus ut minus 1. If you add these two, that is what you get. So t minus 1 ut minus 1 is a proper delayed function of this. Therefore, this is 1 over s squared e to the power of minus s, and ut minus 1 will have the Laplace transform 1 over s e to the power of minus s. So you can see that these three functions have different Laplace transforms. They are not the same time functions, of course. Therefore, we expect the Laplace transforms to be different. You can also see this as this can be thought of as a delayed step plus a delayed ramp. That is what you are having, delayed step plus delayed ramp. Right. Now before we proceed to a discussion of another property, let me caution you about one possible pitfall that one might fall into. We agreed that if the function f of t is delayed by tau seconds, f of t minus tau, this will have e to the power of minus tau s f of s. That is the Laplace transform of this. Now the question that we can ask is, what happens to advance in time? Suppose you have a function f of t, you advance it, so that means f of t plus tau, where tau is once again considered to be positive. Does this mean that this will be e to the power of tau s f of s? This is the question that we would like to ask. We must exercise caution in applying this rule. Why? When you advance a time function, what happens is when you push some part of the time function to the negative values of time, then a part of that function can get lost. Therefore, it is not, if it is delayed, then the same functional variation whatever we had f of t ut continues, but if you advance it in the negative direction, that is a negative direction of time, that means a part of the function can get lost, and therefore whatever is left may not have a complete replica of the original f of t ut. Therefore, this rule may or may not work. So one must be careful in this. As far as Fourier transforms are concerned, the delay, if you have a delay or advance by tau seconds, it is multiplied by e to the power of j omega tau or e to the power of minus j omega tau, as the case may be, without any difficulty, because the Fourier transforms handle time functions which exist for negative values of time as well, but not Laplace transforms. So let me illustrate this by means of an example. Suppose f of t is like this. This is 2 seconds, and then I have, let us say, g of t, which is obtained as f of t plus 1. So f of t is a delayed step function starting at 2 units, and g of t is advanced by 1 second. This is f of t plus 1. The Laplace transform of this is obviously 1 over s e to the power of minus 2s. The Laplace transform of this is 1 over s e to the power of minus s. Therefore, we can see in this case that g of s is f of s multiplied by e to the power of s corresponding to 1 second advance. Therefore, this rule works quite well here, but because when you are advancing this, nothing of this function is getting lost, right? Now suppose you have the same f of t, and now I say g of t now is f of t plus 3. That means this is advanced by 3 seconds. That means it is like this. When you take the Laplace transform of g of t, however, you ignore this portion for negative values of time and take account only of this. So this portion is gets neglected, it gets lost, this portion. So we would say g of s is the Laplace transform. This is, of course, I am taking all this of unit magnitude. So we will take this is the Laplace transform of a unit step function. This is 1 over s. Now f of s as 1 over s e to the power of minus 2s. The function is advanced by 3 units. Therefore, this is not equal to 1 over s e to the power of minus 2s, which is the Laplace transform of f of s. The advance corresponds to 3s. So this would be what we would have expected if the same rule applied for advanced functions as it would apply for delayed functions. So if you had multiplied by e to the power of 3s, you would have got 1 over s e to the power of s, but it is not equal to 1 over s. Therefore, this is not equal to this. This is incorrect expression for this as far as the Laplace transform is concerned. Let me take a third example. Suppose I have f of t, which is a ramp function. So f of t here will give me 1 over s squared. Suppose I advance this by one second. So this I will call it g of t. Now once again, when you are considering the Laplace transform of this portion is ignored, and you are considering only this portion, and that is equal to a step function plus a ramp function of unit slope. Therefore, the Laplace transform of this g of s would be 1 over s plus 1 over s squared, and this is certainly not equal to 1 over s squared multiplied by e to the power of s corresponding to the advance. Therefore, this is not equal to this. So when we are advancing time functions, one has to be very, very careful whether this particular rule like this will apply or not. If the advance corresponds to a situation where no portion of the original function has been truncated, as it has been in this case, then that rule will apply. But in other cases like this, which is more usually the situation, this rule will not apply. So as far as this rule that we have talked about is primarily intended for delayed time functions. When it is advanced, one has to take it with a pinch of salt. The next property we will talk about is scaling. What we mean by this is, if f of t and f of s form a Laplace transform pair, then f of at, where a is a positive constant, that means you scale the time events, you make them appear faster, f of at. This corresponds to a Laplace transform 1 over a f of s over a is the rule that comes. So scaling in time domain also corresponds to scaling in the frequency domain, but in the inverse fashion. If you make events faster, that will be slower, and vice versa, but of course with a multiplying factor here. Proof. Zero to infinity of f of at e to the power of minus st dt. That will can be written as, if you put at as x, this will be f of x e to the power of minus s x upon a dt equals dx upon a. So I will pull this outside. And when t equals 0, x is 0. When t equals infinity, x is also infinity. So all we are having is f of x, instead of e to the power of minus sx, you have x upon a, or s upon a. Instead of st, you have s upon a times x, s upon a times t. X is a dummy variable, you can replace it by t as well. Therefore, what you are having here is, instead of s, you are really having s upon a times this x, which is the variable of integration. So obviously this is the Laplace, if f of s is the Laplace transform of f of t, this would be f of s upon a. Therefore 1 over a f of s upon a. That is what we have proved here. Or you can put this, or a times f a t as the Laplace transform of f of s, which is the same thing. Now this particular rule comes in handy sometimes in numerical working like this. Let me illustrate this by means of an example again. When you have large numerical constants, sometimes we can avoid this by type suitable scaling. Find the inverse Laplace transform of 1 over 10 to the power of 4s squared plus 10 to the power of 2s plus 1. Suppose I ask this question. What is the inverse Laplace transform of this? We have to find this out. So we can scale this in the frequency domain in this fashion. 1 over 10 to the power of 4 s squared plus 10 squared s plus 1 can be written as 1 over s upon 10 to the power of minus 2 whole squared. Suppose I divide this by the same thing, 10 to the s squared divided by 10 to the power of 4, or 10 to the power of 4 if you carry it in the denominator is 10 to the power of minus 4. The same thing can be expressed in this fashion, and then this can be written as again s upon 10 to the power of minus 2, which is same thing as 10 squared times s plus 1. So if I had scaled this s by a factor such that s upon 10 to the power of minus 2 is replaced by s, then this is 1 over s squared plus s plus 1. we know the Laplace transform, inverse Laplace transform 1 over s squared plus s plus 1. Once we know that, we can find the inverse Laplace transform of this by applying the scaling rule. Let us see how we do that. If this had been simply 1 over s squared plus s plus 1, instead of this s upon 10 to the power of minus 2, we would have written this, as we have already mentioned, as s plus half whole squared plus root 3 upon 2 whole squared. Yes, and this would have been 2 upon root 3 times root 3 upon 2 over s plus half whole squared plus root 3 upon 2. Why I put this root 3 upon 2 here is because this is of the form omega naught over s plus alpha squared plus omega naught squared. So this particular Laplace transform would be having its inverse Laplace transform 2 upon 3 e to the power of minus t upon 2 sine root 3 upon 2 t. That is the, of course, u of t will always be there. This is the inverse Laplace transform of this. But now, if this is f of s, what we have having here is, instead of s, we have s upon 10 to the power of minus 2. So we have s upon 10 to the power of minus 2. That is what this expression is. Now, if you go to this rule here, f upon s upon a will be a times f of a t. A in our case happens to be 10 to the power of minus 2. So since we know f of t, we can find out a times f of a t. This corresponds to a times, this is f of t. If this is f of t, this is a times f of a t, where a equals 10 to the power of minus 2. So if you substitute that, you will have 10 to the power of minus 2, 2 upon 100 root 3 e to the power of minus t upon 200 at sine root 3 upon 200. That is the inverse Laplace transform of this. So this scaling rule helps us to make the coefficients, change the scale of the coefficients so that we can handle convenient numbers instead of sometimes unwieldy numbers like this. We can often take advantage of this rule. Remember this is in accordance with what we discussed in the case of Fourier transforms. If you make the events faster in time, this is equivalent to increasing the frequency. That is, if you scale t in one direction, the frequency it goes in the other direction. If t is replaced by 2t, s is to be replaced by s upon 2. So if you compress events time to take them occur at a faster time, the frequency spectrum increases. So you need to encounter higher frequencies. On the other hand, if you spread out in the time domain, then in the frequency domain it gets compressed, the higher frequency components become smaller. So in this lecture we covered 3 important properties of the Laplace transform. The first one we considered was when f of t, function of time, is multiplied by an exponential function of time, e to the power of minus alpha t for example, then in the frequency domain it corresponds to a shift in the frequency variable, that is s will be changed to s upon alpha. And the second important property which we discussed was when you shift a time function in time delayed by tau seconds, the corresponding effect in the transform domain is multiplication of f of s by e to the power of minus s tau. And we saw the ramifications of this if you try to use this to apply to advanced functions. We said when you advance a time function by tau seconds, it may or may not correspond to a f of s which is multiplied by e to the power of s tau. In some cases it may, in most of the cases it may not, because part of the time function may get lost in the process. Lastly, we considered the scaling in time domain, which corresponds to also to scaling in frequency domain. If you are scaling up in time domain, it will be scaling down in the frequency domain by a factor a. Of course, there will be also a change in the multiplying constant. In all these three cases, we have considered various examples which illustrate the usefulness of these three properties when you are evaluating either the forward Laplace transforms or the inverse Laplace transforms. We shall pick up at this point in the next lecture.